Welcome to springlib.
So here, the initial velocity of the car is increased by 50%, and we're trying to find how by what factor does the minimum braking distance change. So we can say that if the mass of the car, mass of m, we can draw a free body diagram for the car. So going straight down is the force of gravity, going straight up would be force normal, and going straight to the left would, of course, be force of friction. We could say that the work needed in order to stop the car would be its change in kinetic energy. And then we also know that the force of friction is going to be equal to the coefficient of kinetic friction times the normal force. And then we can say that the sum of forces in the y direction equals 0, which means that the force normal minus the force of gravity equals 0, giving us that the force normal equals the force of gravity. So at this point, we can say that the only force in the x direction that would be affecting work, so force would be the only force, force of friction would be the only force that is parallel to the distance, to the displacement of the car. So we can say that the work done by friction, which would in this case be negative force of friction times the braking distance d equals 1/2 m vf squared minus v initial squared. So at this point, we know that we're trying to stop the car, so we can say that the final velocity is going to be 0. And we can say that the coefficient of kinetic friction times the force normal. We also know that the force normal is equal to the force of gravity, so we can simply say force normal times mg d equals 1/2 mv initial squared. So at this point, we can say that the distance, the braking distance, is going to be directly proportional to the initial velocity squared. At this point, we can set up a relationship, and we know that the braking distance over the original braking distance would be equal to v squared over the original initial velocity. So here, and we know that the initial velocity is being increased by 50%, so we can say that v equals 3 times v initial divided by 2. And at this point, we can substitute, and we can say that d is going to equal the original braking distance times 3v initial squared divided by 2, rather 3v initial divided by 2 quantity squared, my apologies. And then it would be 1 divided by v initial squared. Those would cancel out, and we would simply have, this would be equal to 9 times the original braking distance divided by 4. So we can say that the distance will increase by a factor of 2.25. So the braking distance increases by a factor of 2.25, given that the initial velocity is increased by 50%. That is the end of the solution. Thank you for watching.